Well, thank you for joining us today. Our speaker today is Peter Tennant. Dr. Peter Tennant is an epidemiologist and data scientist with a primary interest in adapting and translating contemporary causal inference methods into health and social sciences. He is associate professor of health data science at the University of Leeds in the United Kingdom, and we are very excited to have him here with us today. Peter?
Thank you very much. Hopefully you can all see my screen. I'm looking at Kristen just to make sure. That's great. In which case I will get started. I am here to talk about causal inference and directed acyclic graphs. Sometimes a lot of what we do is casual inference. But hopefully by the end of this talk, we do less casual inference than causal inference. My position is that I'm Associate Professor of Health Data Science at the University of Leeds in the UK and the Alan Turing Institute. So today, there's going to be a sort of split session. And the plan is that we have a first session where we kind of think about causal inference in a very, very general sense, and then I introduce these tools known as directed acyclic graphs. And then we take a little bit of pause for questions for about 15 minutes, have a little toilet break, and then return for the second half, where essentially we do the same again with a more detailed discussion of kind of using directed acyclic graphs in practice. And then again, 15 minutes of questions and answers at the end. The plan is, because we're expecting quite large numbers and we want to make sure we get the best use of time, that you submit your questions into the chat box. And then my colleague, Georgia Tomova, who's also here, will try and select a kind of range of questions to be asked during those periods. But we will try and ensure that everyone's question is answered. So if they can't be answered here on the day, then I'll basically type a response and then hopefully provide that within the kind of post-presentation materials, so that if you have any question and you submit that question with the chat box, it will get answered in due course. So I was approached to essentially provide a presentation on what is causal inference. And I actually find this quite a difficult question to ask for a number of reasons. But one of the reasons being that often, in order to answer what is causal inference, you first have to describe what it's not. But I'm going to take you through a little bit of a journey, hopefully, that will help to make that, to give you an answer to that question. And the first part, really, I think it's useful to start with, what does this mean as a human rather than as a scientist? Because the good news is we all implicitly really understand causal inference, because it's something that we all learn and develop from pretty much the moment we're born, if not probably even beforehand. We tend to associate objects and actions in the world around us with consequences. And whether that's passively, literally by kind of observation and experience and learning, no, I don't really like this very much, or whether that's actively by trial and interaction and learning, gosh, look what happens when I interact with the world. And all of that kind of knowledge and all of that thing that's happening all the time from the moment you're born is essentially encoded into a growing and improving mental model of the world. This is like a little model that collects together all of the rules of the way that the world works within your head. And the wonderful thing about that model is it's so sophisticated in terms of its understanding that you can actually use it to simulate. You can use it to ask hypothetical questions about, what might happen if I do this, and you can use it to ask counterfactual questions. How could things have been different if I had behaved differently? And arguably, that ability for us to consider kind of the hypothetical world and the counterfactual world is what has allowed us as human beings, for better or worse, to make such dramatic changes to the world around us, because clearly our ancestors perhaps never would have imagined the world as it exists today. But at each point along the journey from there to now, somebody has imagined a change that has then been implemented. But from a scientific point of view, there are a couple of limitations with this kind of mental model process. The first is that it is extremely strongly tuned to make causal inferences. From a scientific point of view, arguably massively overtuned. So perhaps because this confers a survival advantage to be able to infer a causal relationship from very, very limited data, we tend to do this throughout our lives all of the time. And in that sense, we are not actually very different to the animal world. We're not very different to Pavlov's famous dogs, in that who in their case learned to associate the ringing of a bell with the arrival of food and therefore began salivating simply when they heard that noise. We have a tendency to do the same, to infer causality from coincidence. And it's for that reason that we have such kind of a large and rich history of superstition, such as that tendency, if you wear a particular item of clothing to a sports game, particularly if you take part in that sports game, and then you do well, you might decide that that item of clothing, that hat, is your lucky hat, and start wearing it all the time, and decide you can never even wash it, because we like to find these kind of causal explanations for what's going on and then try and use them to influence our world. And the beauty of that is it also causes quite a lot of humor when we make over causal inferences. So this is an example where this seagull is very unlikely to be a particularly unheavy seagull. It's far more likely that it's just perched itself conveniently on that little dip there of the pipe. But because our brain is always looking for that causal explanation, it's amusing, because we think, oh gosh, look, that's look what it's done, even though we know that's not the case. So then the second problem that we have is that that engine struggles as soon as, in a sense, it requires far more data than our empirical experience can provide. And really that happens when cause and effect relationships are not deterministic. So a deterministic cause and effect relationship is one where essentially A plus B always equals C. And a good example is something like an infectious disease that essentially always leads to symptoms. So here's a healthy individual. If they were to contract Vibrio cholerae, then for a deterministic process, we can be pretty confident that they would end up being unhealthy. And so our brain is quite confident with the idea of understanding, okay, this bug, Vibrio cholerae, is the thing that caused this disease, cholera. The problem is it struggles as soon as that relationship is not, universal, is not deterministic. So when we have a healthy individual who smokes, our mental model of the world might tell us, okay, they're more likely to die early, or they're more likely to experience health problems, or all the rest of it. But it might also struggle with the fact that that's not universally the case, that there are these counterexamples. And I certainly know in the wider world and in the public, these non-deterministic cause-effect relationships cause a lot of confusion about whether or not they're true or valid. Luckily, as scientists, we have developed a very helpful tool to help us, in a sense, resolve that problem. That is statistics and probability. And together, they allow us to turn something that is completely unknowable for an individual. So, for example, we cannot know what will happen, what will be the total sum if we were to roll a pair of dice, into something that is predictable. In other words, we can know what the likely distribution of scores will be if we were to roll 100 pairs of dice, or a pair of dice 100 times, more realistically. We'll never be 100% spot on, but we can get very, very close to what the distribution is expected to look like. The handy thing is that when we combine that with this other kind of tool, randomization, then we can actually estimate these probabilistic causal effects, the ones that perhaps intuitively we wouldn't be so good at, really quite effectively. If we assign some intervention, some treatment or therapy at random between a large enough group of individuals, and then compare what happens to those two groups, we can be pretty sure that the difference between them is likely to result from the assignment that we've made, as long as we have large enough numbers. And this tool, which actually is not very old, randomization, has proved so powerful and so useful that understandably it has become embodied as the kind of pinnacle of and the gold standard way to estimate causal effects, particularly in primary studies. So the primary way for us to go out there and answer a causal question really is to try and conduct a randomized controlled trial. And for that reason, it's been encoded in the health and medical community as the gold standard approach. It's been encoded such that although there are more modern versions of these two representations, the triangle on the left and the table on the right, the essence is still the same. That people are generally taught randomized controlled trials are the best thing, and then as you move away from that approach, you should be increasingly skeptical about the quality of the data and the validity of the results. Now, that's probably fair enough, to be quite honest, because when it comes to trying to answer causal questions in non-randomized data or in observational data in particular, we have somewhat of a mixed record as a scientific community. This is a very contrived example, but nevertheless, the authors, I guess, were attempting to prove a point. They looked at 52 claims that had been made from observational data, and they looked at the results of 12 randomized controlled trials, which has sort of answered those claims. And they reported them, and they found that none of those claims were replicated, and 5 even found the opposite. Now, in fact, these 52 claims are 52 of the most famous failures in observational science. So if we were to conduct the analysis in a more random fashion, I would not expect such a tragic record. But clearly, there have been occasions where the results of observational research has been disappointing and perhaps even catastrophically misleading. And that has led to a relative lack of confidence in our ability to ask causal questions when we're not using randomized controlled trials. It's perhaps for that reason, or just more generally because this is known within society, that we are drilled with this message. Correlation does not equal causation. And we're not just drilled with it. There's a whole kind of meme community focused on trying to provide amusing examples, like the seagull example, where correlation does not equal causation. There is this website, for example, where you could see that per capita cheese consumption is ridiculously strongly correlated with the number of people who died becoming tangled in their bed sheets. It's a great example of a relationship that almost certainly doesn't have any causal process taking place, but nevertheless is convincingly strong. So again, as an extension of that, the medical kind of research community encourages that in general, we don't even use causal languages unless we're conducting a randomized controlled trial. So if you're conducting an observational study, then really you should not be talking about cause and effect. You should be talking about association and correlation. Again, that idea is sort of encoded within our evidence appraisal tools. So this is just a tiny section from the so-called grade criteria. The grade criteria is used by evidence synthesizers to try and judge how confident we are in the quality of a piece of research. And it automatically decides if a study is observational, the quality is low. There might be some caveats to that, but essentially that's the algorithmic process. And as a consequence of all of this, we as scientists have been taught to rely on euphemisms rather than talk about cause and effects or causal relationships. We tend to talk about links and associations and predictors and risk factors and correlations instead. But that is actually quite problematic for two key reasons. Spurious correlations in themselves have no scientific value. I mean, the fact that per capita cheese consumption is spuriously correlated with the number of people who died by becoming tangled in their bedsheets doesn't really help us if, as a public health practitioner or a healthcare practitioner, we want to reduce the number of deaths due to bedsheet tangling. So that's not scientifically actually that useful. And the second thing is to come back to the beginning. We as humans are not too dissimilar to Pavlov's dog. When we see a correlation, we have this tendency to salivate, to start drawing these causal conclusions, which we've termed Pavlovian causal inference. Whenever we see a correlation, even when we know we shouldn't. So even though we know per capita cheese consumption and number of people being dying from becoming tangled in their bed sheets is almost certainly a purely spurious correlation, there is a tendency to sort of wonder, could it be, you know, that eating cheese at night, doesn't that cause nightmares? Maybe if you have nightmares, you're more likely to end up tangling yourself in your bed sheet. That tendency is so strong, so strong that even as really well-trained scientists, it's almost irresistible. And so what tends to happen at the extreme is a wonderful combination of simultaneously saying that causal inferences cannot be made whilst making causal inferences. So we call this Schrodinger's causal inference. It's simultaneously not possible, yet we'll make it nonetheless. And there's an example which I stumbled across on social media a few years ago, I guess because it was an interesting study, but they declare early on in their discussion, findings are based largely on cross-sectional data and thus causality cannot be inferred. And then in the next paragraph, they spend the entire time basically explaining the policy implications, which doesn't make sense if causality cannot be inferred. If really it should say causality cannot be inferred. These are spurious correlations. They are of no value in the real world. But of course, they know that's not really what they're interested in. And that problem of Schrodinger's causal inference is very common. So I was very fortunate enough to be involved in this large review that was conducted over the last 2 or 3 years by Noah Haber and colleagues, as you could see, in the American Journal of Epidemiology. And that looked at over 1,000 different health and medical articles from, I think, the last 10 to 20 years, and basically examined the language that they used and whether or not causal inferences were made. And we found a substantial disconnect between the causal implications used in the technical linking language, in other words, in the kind of methods and discussion, and the research implications, in other words, in the discussion and the abstract. And so this problem of Schrodinger's causal inference is common. But when you think about it scientifically, it's ridiculous for us to be saying, on the one hand, these results shouldn't be interpreted causally, and then the other going and making overt causal inferences. So it's for that reason that in 2018, Miguel Hernan and others in the American Journal of Public Health at that time recommended a change, which is that rather than this mantra of correlation does not equal causation, we're only interested in correlation and association, to actually admit and to accept and admit our causal ambitions, to embrace what he termed the C word, causality. And he makes this very strong argument, which I've reproduced verbatim on the right here. The prescription against the C word is harmful to science because causal inference is a core task of science, regardless of whether the study is randomized or non-randomized. And without being able to make explicit references to causal effects, the goals of many observational studies can only be expressed in this kind of roundabout way. And the resulting ambiguity impedes a frank discussion about, in a sense, the appropriate methodology that we should use. So for that reason, writing, I think 4 years later, we recommended in our article that rather than policing which word people use to describe their causal relationships, we should instead recommend focusing on better ways to identify and assess causal inference based on the study designs and the assumptions. So don't just use roundabout words, use the appropriate methods instead. That, of course, then leads to the question, well, hang on, what are the appropriate methods and what is this concept of quantitative causal inference if it's any different to what I've been doing for the last 30 years? And again, even focusing now scientifically, this is still not an easy question to answer without first saying what it's not. So I tend to go back to what is data science? What is the larger framework in which causal inference takes place? And that starts with what is science? Well, science is about building knowledge and understanding. And therefore, data science is about gaining insights and extracting meaning from data. So most data science activity, and this is something Miguel Hernan has argued, can be divided into 3 scientific tasks, each of which then have different methods and philosophies. And those 3 tasks are these 3 things: description, prediction, and causal inference. And in a sense, you guessed it, causal inference is not description or prediction. And I'm just going to briefly describe what these 3 things actually are. So description, which I think is very much undervalued, but is extremely important, is the scientific task focused on summarizing, describing, and visualizing features of data. By definition, it's data-driven. We tend to, in a sense, conduct very simple calculations, such as our prevalence and our incidence, and we might conduct unsupervised learning in order to look for kind of clustering or patterns within the data. And the kind of questions that we would ask with a description approach is, what happened? Or what was the occurrence of some outcome in people with some condition? Moving on from description, we then have prediction, so or otherwise known as classification. And this, rather than just focused on describing how things are, is focused on recognizing patterns and making forecasts about the future. So again, this is very data-driven. This time we might use a lot more sophisticated tools. So whatever statistical modeling or supervised learning approaches are your favorite methods are probably the kind of methods that you might be using within the prediction world. And this time, again, rather than just describing, we might be asking questions like, what will happen, or what might happen? What is most likely to happen? Or are people with a particular condition more likely to end up with a particular outcome, rather than just having more of that outcome? So finally, we're able to define causal inference as distinct from these 2 things, otherwise known as counterfactual prediction, as something that is focused on gaining understanding. And the crucial feature that is different from the other 2 is that this is fundamentally not purely data-driven. It involves a fusion of external knowledge with our various kind of modeling techniques and data. And so this time we ask questions like, what will happen if? And if we were to change something, how would it change something else? So the sort of key message from that is that we can use data-driven algorithms to find patterns in complex data. And so, in fact, they're extremely good at that, and they're therefore very, very well suited to prediction. But that if we're seeking causal inference, scientific causal inference, quantitative causal inference, whatever you might call it, this is different. This requires that we that we identify and estimate counterfactuals within our data. Well, they're not something that can be learned from the data alone, because by definition, counterfactuals aren't in the data. They're only things that we can estimate from data. So in order to answer these kind of questions, instead, we have to provide some external knowledge, whether that's by controlling the data generating process directly and conducting an experiment, or whether that's knowledge of the data generating process. And what I mean there is knowledge of the story, the backstory of how that data came into being. And the reason we have to provide that is that algorithms see really what's in red on the left. They see correlations. They see a whole bunch of variables that we might call a whole bunch of variables that we might call predictors, and then a single outcome that we might call a single variable that we might call our outcome. But we know that, in fact, those variables did not just occur all at the same time, that there was actually some story behind their creation, with one causing the next and so on and so forth. And that we have to provide that information about how nature created the data in order to start to answer causal questions. Now, what's handy is that there are actually methods that have been made available in order for us to do this, because if I was to give this presentation 50 years ago, I would start to run into problems of, well, this is a nice idea, but we don't know how to do it. Luckily, since particularly the turn of the millennium, although they've existed from before then, there has been a real kind of a growth in a series of different tools, which we might call contemporary causal inference methods. And probably the two most prominent are the potential outcomes framework and the structural causal model framework. And the structural causal model framework was developed by Judea Pearl on the left, who's pretty much become sort of renowned as the originator of modern causal inference. And what these do is they provide a formal framework for us to actually start to think about causality and causal effects. So, which combines probability theory, counterfactual reasoning, and graphical model theory. Now, the key feature of a causal inference approach, which makes it different to perhaps alternative approaches to data analysis, and perhaps the one most important lesson from today, is that it separates the process of identifying the thing we want to know from actually then going and estimating that thing. And so this is known as the identification and estimation separation. And then within that, I'm just going to sort of go through the different steps that involves, with the analogy of trying to make a cake. So we start with the thing that we want to know, the goal. In other words, the causal effect of interest, which we call the causal estimand. This is like this Olaf cake that I've decided I would really like to try and make. What we then do through the process of identification is we try and identify a blueprint in order to estimate this cake, in order to bake this cake. So this is where we come up with our schematic. And this formally is known as our statistical estimand, because that is the estimand that we can use within our data to actually try and estimate the causal estimand, which is sort of the theoretical aim. From that, we are then able to construct an estimator, which you might think of as our recipe, and apply that to data, which you might think of as our ingredients. And together, those two things, ta-da, then produce your estimate, which is your best attempt to try and produce the thing that you set out to make to begin with. And I can confirm that the cake on the right is not a stock image or is not a Pinterest failure. It was actually my birthday cake from last year, where colleagues attempted to produce a version of the causal estimand on the left and came up with a rather wonderful analogy for the realities of how hard it is to actually do this process. So I've used the word estimation And the reason I've used the word estimation is just also to highlight that this is philosophically different to the standard approach that many of us will have been brought up with in scientific research, which is testing. So testing is something that's focused on asking binary questions of whether or not, for example, a significant effect was observed. So most commonly, we would conduct null hypothesis significance tests in order to ask, is our data significantly different to some null distribution? And the problem with this approach is that it encourages quite a few bad practices, such as p-hacking. So estimation, which I think a lot of people encourage to be a key part of causal inference, is quite different. It's focused on obtaining merely the most accurate estimate and the most accurate estimate of the uncertainty around that, acknowledging that no single study will ever stand alone. So this is far less glamorous, perhaps, than asking a binary question, does or this cause this, yes or no, and clearly places a lot more trust in the idea of accumulating collective knowledge as a scientific community, but hopefully also encourages better practice, such as quantitative bias analysis, which is where we ask, how can we improve our estimates based on external information that's not available within our data set? So the key from this is that hopefully we move away from asking this kind of thing, which is we sought to identify risk factors for Y, and we found a significant independent association between X and Y. There's many problems with this, including the word risk factor. I would encourage people not to use that term. And if they want to know why, have a read of this lovely article by Anders Heutfeld in the BMJ. But regardless, the idea is to move away from this kind of yes or no significant question making towards a more descriptive focus on estimation. So we sought to estimate the total causal effect of X on Y in population Z, and the estimated total causal effect of X on Y in population Z in our data was this, with this uncertainty around that. So that's the kind of high-level philosophy. The main tool that we use for this is the directed acyclic graph. So this is a type of causal diagram which really helps us with that process of identification of turning our causal estimand into a statistical estimand. And the reason for that is it allows us to encode that necessary theory about the data generating process. So these are non-parametric graphical representations of the causal relationships between variables that we think exist. And they include a number of different features, anatomical features in a sense, which I'm just briefly going to whiz through in the next few minutes before we have questions. So they have nodes, which essentially represent variables, and this is A to F in the diagram on the right. And then we draw our hypothesized causal relationships between them via these arcs or arrows. And then one of the key rules is that there's no circular paths between them. So why are they directed? Well, they're directed because causality is directed over time. A cause cannot occur after a consequence. So if we have this relationship X, Y, and we draw this arc here, then we are making a number of key statements along the lines of the following. We are saying that by drawing this arc, changing X would modify the probability of Y. We are also saying that if X had been different, then Y would have been different. Or more generally, Judeo-Pearl would say, we're just saying that Y in some way listens to X. Or visually, if we were to wiggle X, it would wiggle Y. Okay. So, as I say, I'm just going to whiz through some of the key anatomical features of these tools right now. So the first thing is we have a path, and a path exists between two variables, any two variables that are connected by one or more arcs. Doesn't matter about the arrow direction. So there, DFE is a type of path. Paths then may exist in two states. They are either open or closed. And an open path will transmit a statistical association or a correlation, a dependency, and a closed path will not. So in these two extremely simplified diagrams, because there's an open path between X and Y on the left, then they will be correlated. Whereas because there's no path between X and Y on the right, they will not be. So in terms of types of paths, obviously the most important is a causal path. And this is where all the arrows run in the same direction. So here we have A to C to D, and that means that if we wiggle A, it would wiggle C and then in turn wiggle D. A confounding path, and these are perhaps the most important to know about in practice, or backdoor path is one where the arrows don't flow in the same direction. Instead, they flow backwards to a common ancestor that we call a confounder and then forward. And the important feature of a confounding path is that without conditioning, and I'll explain what that means in a second, confounding paths are open and will transmit dependencies between the variables between them. Due to that confounder A. So due to that A at the forking point. So that means if I was to wiggle A downstream, it would cause C and F both to wiggle together. And of course, if we didn't know that was due to A, we might assume that they were wiggling together due to causality rather than confounding. The way that we get rid of this, in other words, is the way that we close these confounding paths is that we condition on that common ancestor, the confounder. So here A has been conditioned upon, and because it's been conditioned upon, we've stopped that common correlation between the two variables. So conditioning, just for reference, is the process in which we estimate a statistic at fixed levels of one or more other variables. Okay, and there are many common ways to do this, but the three most common are restriction, which is where we estimate in a subsample of some variable where we choose only one level of that variable, so it might look only at non-smokers. Stratification, which is where we estimate within strata of some other variable, such as non-smokers, ex-smokers, and current smokers. And then probably most common in practice is covariate adjustment, which is where we actually control for values of these variables by including them as covariates in a linear regression model. So we might include smoking status as a covariate in our model. You'll also come across matching and weighting, which are increasingly popular and important. So I just want to give an example of confounding and how conditioning close confounding. This is possibly the most famous example in the world, which is that apparently in many data sets, you could see a relationship or correlation between ice cream sales or ice cream consumption and the incidence of a shark attack. Now, it's very unlikely that that's going to be causal. It's far more likely that it's caused by a common ancestor, common cause, weather, and weather therefore acts as a confounder, and because of weather, because of hot weather, meaning you're more likely to eat ice cream, and hot weather, meaning you're more likely to go swimming and then encounter a shark, then you see this correlation between these two variables that otherwise have no place being commonly correlated. So we can resolve that correlation, we can close that backdoor path by conditioning on that confounder, in this case, weather. In other words, if we were to look only at hot, sunny days, we would not expect there to be that common correlation due to the weather. We would not expect there to be a relationship between ice cream and shark attacks. So the final thing I just want to mention before we open to the Q&A is this, a collider path. So this is another type of path that changes direction, initially flowing forwards to a common descendant and then backwards. So here we have an example, A, C, D, F, E. And the rule is that without conditioning, collider paths are closed and will not therefore transmit dependencies either side. So if we were to wiggle A, it would get to the collider F and then stop. However, if we condition on a collider node, we open the collider path, and that then creates an interesting type of sort of mirrored conditional dependency either side. So what would happen if we're conditioned on F, we wiggle A, it passes through F and it almost goes through into a mirror world and comes out the other side, kind of wiggling in the opposite direction. So to give an example of this, I've chosen the extremely non-controversial mediocre white male problem, which I'm safe to say, because no one's around me at the moment here in the University of Leeds, is certainly a problem here. So the idea behind this problem is that we could imagine there are two competing causes of career success, privilege and talent. Success such as achieving tenured faculty position, and that in the general population, we would not necessarily expect these two things to be related. However, if we were to only look at people who had achieved career success, in other words, if we conditioned on the collider here in this diagram, we would expect to introduce one of those strange mirror dependencies between the amount of privilege and talent required to achieve career success. We would expect an inverse association that would then look something like this, where individuals who have achieved career success either have very high levels of privilege and surprisingly low levels of talent, or very high levels of talent and surprisingly low levels of privilege. So that's confounding and collider bias. In the next part, we're going to learn about how DAGs can actually be used in practice to identify our statistical estimand and therefore conduct our data analyses. But I'll just summarize, and then Georgia will have a look at any questions that you've asked. So in summary, as humans, we're naturally overtuned to make causal inferences, but this doesn't work very well when we're dealing with non-deterministic causation. So as scientists, we've tended to learn that correlation does not equal causation. And so we've become discouraged from using any causal language and even from admitting when we're seeking to estimate a causal effect. A better approach would be to embrace our causal aims and then recognize that causal inference is a distinct task that requires distinct methods. Those methods then involve separating the process of identifying a causal effect from actually estimating those. And DAGs, which I haven't fully introduced, but so far I've introduced the idea that they theoretically provide a transparent means to identify our assumptions and therefore help us identify the statistical estimand that we need. So I'm going to stop sharing my screen, and then we're going to open the floor to questions. And hopefully some of you will have already submitted some questions, and hopefully Georgia will be able to start to have a look at, if you haven't, feel free to start typing questions in the box, and we'll see if we can answer some of those in the time that we've got. Right, Georgia, over to you.
So currently we have two questions, which I think you'll be very happy to answer. The first one says, great talk. What should we do with the millions of studies of risk factors to something? Any comments about that? Improving our understanding of those studies, just considering those as associations without any causal interpretation? Question.
Wow, that is a wonderful question. Which there is no easy answer, because in a sense the really easy answer is we throw it all away and say, I'm afraid we can't trust any of this because it didn't use appropriate methods. That's not really acceptable. Oh, it's certainly not likely to be acceptable to a lot of people in practice. So I suspect what we will have to do is develop a better approach to be able to appraise the quality of that evidence. And the reality is that although these studies of risk factors will not necessarily have used appropriate methods, some will have used far better methods than others. Some will have considered their confounding adjustment set, albeit with traditional methods, they'll have done so a lot more carefully than others. Some will have committed serious analytical problems such as table 2 fallacy, which I introduced in the next slide. Others will not. So the evidence appraisal process probably needs to change when it comes to observational studies. We probably need to get a lot better at working out how best to judge these kind of old traditional studies. I suspect, and this is something I'm very interested in sort of developing guidelines on, the ideal would be that you as a reviewer and a team draw a DAG for a particular research question, and then you go through the existing evidence and you start to sort of judge, well, okay, which confounders have they adjusted for and which ones have they not adjusted for? And if they haven't adjusted, can we kind of rescue the estimate with some quantitative bias analysis, et cetera, et cetera? It's likely to be quite a lot of work for us to, as a community, first of all, come up with some of these recommendations, and secondly, to actually turn that into more practical guidelines. Just to finish the question, I'll, because I've noticed no new questions have come in, so I might as well.
They're coming into me, so you do have more
you.
questions, yeah.
All right, okay. Okay, that makes it. There is a systematic review that recommends a sort of matrix approach to really drilling down and working out, have they used an appropriate adjustment set, so on and so forth. Okay, I'll hand over to Georgia for the next question.
Yeah, so next question is, thank you for the talk. You mentioned earlier that the graphs must be acyclic. However, we certainly have processes that we're interested in that are cyclic. How could we use this approach to estimate cyclic processes like feedback loops?
That's a very, very important question. And I apologize for my lack of clarity there. So when I say that it's acyclic and you can't have a cycle or a loop in effect, I mean that a variable cannot cause itself at the same moment in time. Okay, so we can't have a single measure causing itself, right? But we can have a variable evolving over time with kind of multiple versions going back and forth. So in terms of kind of looking at those kind of complex variables, what you end up with is a long DAG of the world evolving together. And from that, you can then start to try and ask questions about these kind of feedback loops and these time evolving processes. I hope that makes that clearer.
Thanks. Next question is, how do DAGs differ from complexity approaches which see patterns based on emergence in seemingly random systems over time? And do DAGs have a place in complexity analysis of large systems?
I would definitely say that I think the DAGs have a place. They have a very strong place, ideally, in complex system modeling. Clearly, the problem is that it's very easy to draw a simple DAG. And then as soon as you're actually trying to describe that complex system with all its different parts within a DAG, you're going to fall down and face some real practical challenges. We haven't resolved those very well yet. What it may be is that we have to learn to get better at sort of pruning our DAGs and focusing on the bits of the DAGs that matter, if that makes sense. In terms of how they sort of compare to some of the methods that are used, like agent-based models or microsimulation methods, the DAG theory is actually very, very similar to, in fact, it's identical to conducting microsimulations. Agent-based models assume a very special form of kind of time-evolving interaction. And at the moment, these are not very well implemented within DAGs. So at the moment, we haven't yet worked out a nice way to sort of model these things, but there's enormous interest in this. And so I would say, obviously, watch this space rather than DAGs have no place in complex system world. It's literally, there are many, many people around the world conducting this kind of work to try and unify the two approaches, I think.
Thank you. So the next question says, this may be covered in the next section. I don't think it is, but do correct me if I'm wrong. How do DAGs differ from path models?
That's a very, very good question. I actually get asked that question a lot. Technically, a path diagram is a sort of parametric DAG. But on paper, until you've actually done the simulation, or until you've actually done the analysis and got some path coefficients and all the rest of it, they're basically the same. If you look at a path diagram that you've drawn as a theoretical diagram, it's a DAG, right? When you then conduct a path analysis or a structural equation model, it makes a number of assumptions about the sort of nature of the relationships. The most obvious being, it assumes kind of linearity, it assumes additivity, etc. So that's sort of then moving from this non-parametric world of just describing causal relationships in very qualitative terms to a parametric DAG, if that makes sense. So in practice, probably a lot of people who use path models are quite used to drawing DAGs. They just haven't necessarily learned all of the same language that comes with DAGs. And the thing that I would flag up in particular is most people I know, including myself, because I grew up using path diagrams, will not necessarily be so familiar with collider bias. And that could be one of the big problems that is kind of overlooked sometimes.
Thank you. So there are two more questions that I think you can also see in the chat. The first
Wonderful.
one says, how does the need to evolve the language used to describe statistical associations impact translating data for public knowledge? For example, risk factor as a term for the public.
That's a really good question. And actually, someone in the UK emailed me only last week to ask about the sort of challenges of trying to communicate causal inference to the public, because it's new. We don't have this history of doing this. I think we do need to conduct some patient public work, really, in order to work out what people understand when we talk about different concepts. I think clearly people are quite happy with X causes Y when it's come from an experimental study. So they might be okay with us saying exactly the same as long as we've used appropriate methods within an observational study. So some of these terms like risk factors, we have evolved because we know that we shouldn't, that we can't really declare a causal relationship. But if we've got better at doing that, then perhaps it's okay for us to do that. That's something we need to sort of test. I think I think in terms of risk factor, do the public really understand it that well? I don't understand it that well. I mean, I suppose it's something that is related to your risk. Of an outcome, so the older you are, that's a risk factor for a number of different things. But when you actually really probe underneath that concept, it's quite difficult to know what that really means. Does it just mean I'm at a higher risk? Or does it mean, do people interpret that to mean something they could change? I suspect we can actually come up with better terminology. But it again, as with almost so much causal inference research, we actually need some more research here to sort of address that properly, to work out what terms make sense to the public.
Thank you. There are two more questions. I think we have time for both. Yeah, and also I must say all the questions have been excellent. So the next question is, do you see a shift for journals outside of epidemiology accepting descriptive studies that focus on estimating, point estimate and variability rather than statistical significance?
Do I personally see a shift? I don't. My sample is too small, and certainly I wouldn't say I've seen any shift in terms of what comes up on my feed and what I tend to see coming out. I still tend to see an awful lot of research, even causal research, that's relying on statistical significance testing. That said, in my personal experience, both as reviewer and as writer, I have found clinical journals to be very, very reasonable in responding to the request to remove statistical significance testing. So if you as an author say, we don't do this in causal inference, they tend to be okay about that. And likewise, as a reviewer, obviously, when I say, I'm sorry, you shouldn't be doing statistical significance testing, again, the journals tend to be okay. They tend to accept it's a little bit like the old days when Bayesianism was new, and they just think, okay, it's a different world there. It's a different world with causal inference. They sort of, I'm not saying that's going to be universally the case, but I think there's a lot more comfort. Did you say there was one more question, Georgia, or have I?
Yes, there is, and I think we have time for exactly one more question.
Amazing.
But if anyone else has comes up with any more questions in the meantime or during the second talk, just send them to me, and then Peter can answer in an email after. So last question. So Perl largely builds on non-parametric structural equation models that are represented in DAGs. And this allows for estimation of causal inference while controlling for unknown or even unmeasured confounders in observations, from my understanding. How can this approach be generalized to nonlinear parametric modeling of processes? Could the causal effects of parameters in nonlinear models be determined through simulating the output of the model with different values for parameters, or should we still try to control for confounders similar to Perl's approach? Let me know if you want me to repeat any parts of this.
No, I'll do my best at answering this question. It's a little bit more technical. So it might be easier answered with some thought rather than on the spot. My on the spot thought is that actually there's no rule about linearity or the parametric shape of a relationship between a variable X, Y, etc. When we draw a DAG, it's completely non-parametric. We are not making any statements about the nature of any of those relationships, whether they're additive, whether they're linear, all the rest of it. All we're saying is, in theory, these things cause these things, and these things need to be controlled for or conditioned on. Clearly, you need to use the appropriate parametric approach in order to do that. If you linearly adjust for a relationship that is nonlinear, you will have residual confounding. So I would kind of argue that in general, there's no kind of linearity assumption or anything like that built into DAGs. But perhaps it's often overlooked as to how important it is to think about the nature of those causal relationships and to make sure that they're well kind of accounted for when you're doing your modeling. I hope that answers that fascinating question. What I'm going to suggest now, because I think all of us, it's always a good idea to have a very brief break, is that anyone who needs a loo, get up, have a stretch, come back. I will start promptly at 5 past the hour. So we've got about 4 minutes exactly before I'll start speaking again. And I'll see you again very soon for the second half. Okay, we are coming up to 5 past the hour in the next 15 minutes, so 15 seconds. So just warning you in advance that I'm about to jump into the next session to make sure that we get through all of the content. Because this time in the second half, I'm going to try and focus on some of the more practical aspects of sort of designing and using DAGs. So in the first session, we learned one does not simply imply causation from correlation. And ideally, as an extension from that, more importantly, we learned that one follows this approach, the sort of contemporary causal inference approach of identifying, well, first of all, defining what it is that we want to estimate, our causal estimand, then through this process of identification, finding a blueprint in order to estimate that. That's our statistical estimand, which we can then use to construct an estimator, or our recipe, which we apply to some data in order to produce the magnificent estimate on the right there. And I said that DAGs can help us to identify assumptions about the data generating process. And the reason that that's useful is that that then helps us to identify the appropriate statistical estimand and in turn select an estimator. So in other words, they really help with that process of working out what it is that we need to actually do in order to estimate a causal effect. So to go from the left-hand side to the right-hand side. Now, I will return briefly to some suggestions about drawing, using, and reporting DAGs later. But really, I just want to focus on the sort of, and I might labor this point quite a lot, but the main message really is that in order to estimate a total causal effect, say, of an exposure on an outcome of X on Y, which we might call our focal relationship, then we just need at the core, we need a very simple rule that we want all the causal paths to be open and we want all confounding paths to be closed. So that means that we want to identify all of the things that satisfy the definition of a confounder, and then we want to condition on those things. So in this case, U and C. However, the role of every variable is intimately defined, in fact, fundamentally defined by its relationship to the focal relationship of interest. So the focal relationship is the exposure outcome relationship. In other words, if we're considering the total causal effect of X on Y, our exposure is X and our outcome is Y. Until we have defined that focal relationship, no other variable has a role. It doesn't have a name. There is no such thing as a confounder. There is only a confounder for the causal effect of a particular exposure on a particular outcome, if that makes sense. So once we have defined the focal relationship within a DAG, we can then give names to the other variables and describe the roles that the other variables take. So that's where they turn from gray into these different colored categories, which I'm going to whiz through briefly. So clearly the most important category of variable, the ones that really in practice we spend most of our time drawing DAGs in order to identify, is confounders or primary confounders. And they are things that cause both the exposure and the outcome. If you remember, they are the forking point in that road, such that if you were to wiggle them, they cause a common wiggling of both the exposure and the outcome. And it's that confounding bias problem that we're trying to identify and get rid of. We also have these variables known as mediators. These are things that are caused by our exposure and in turn cause the outcomes. So they are along the causal path. They are part of the causal mechanism in which the exposure causes the outcome. They channel part of that total causal effect. We would not want to condition on these things if we're estimating a total causal effect, because they're part of that effect. And then there were these two kind of lesser known members of the family. One is the competing exposure. This is something that causes the outcome, but is completely unrelated to the exposure. And then kind of its sibling is the instrument, or the instrumental variable. And that's something that causes the exposure, but is unrelated to the outcome except through the exposure. So the broad idea, as I've highlighted, I'm going to labor, probably over labor, is that we want to identify, measure, and conditions on our confounders. So once we defined a focal relationship, we want to work out what are the confounders. In this case, it was U and C, and then we want to condition on those in order to estimate a total causal effect. In practice, of course, we're going to encounter a number of different problems. The first of those is that there will inevitably be some confounding variables that, for whatever reason, are either unobservable or we simply were not able to observe in our particular data set, and therefore we could not directly condition on. And so these unobserved variables, and in fact all unobserved variables, can be depicted with circles and ellipses. And this, for those who've used path diagrams or structural equation models, this is generally the notation that's used in that setting. Observed variables are squares or rectangles, and unobserved variables are circles or ellipses. So here, U is an unobserved confounder, and it's therefore causing unobserved confounding between X and Y, because we haven't conditioned on it. So what do we do about this? Well, the first thing is we can try and look for downstream variables that exist on that confounding path that would block that we can use to block that confounding fact. So here, U acts on Y entirely through this variable U2. Okay, and U2 is something that we're actually able to measure. And so in theory, measuring and conditioning on this thing, U2, would completely eliminate the confounding due to U, right? So that backdoor path, X, U, U2, and Y would be closed by conditioning on this variable U2. This type of confounder here, U2, is known as a secondary confounder because it doesn't directly cause the exposure and the outcome itself, but if we were to condition on it, it would completely close the confounding due to that path. In practice, I suspect that secondary confounders don't actually exist in the real world. As certainly they're not very, very likely to exist. And that's why really we can just refer to confounders rather than primary and secondary confounders. And the reason for this is that in practice, I think it's very likely that confounders, like all variables, will act on other variables through a whole range of different mechanisms. It just seems completely implausible to me that there would ever be a single variable through which all of the mechanism acted, as with U2 in the previous example. So here, U2 no longer completely explains all of the mechanism through which U acts on Y. And therefore, if we were to condition on U2, it would only partly block that backdoor path. U2 is therefore what we would call a surrogate confounder. It is a surrogate variable that we can use to reduce the confounding by U, but not completely eliminate it. And what's left, the leftover confounding that remains after we've attempted to correct for confounding, is the residual confounding. So here we have some residual confounding left over because XUY has not been completely blocked. Now, in practice, you will have residual confounding from every single confounding path that you try and block. And the reason for that is that even though in theory conditioning will block every path, in practice, you will always have an imperfect measure of the variable. And so when you adjust for it, when you condition for it, it will only partially remove the influence of that variable. And so in this example here, you could see some of C and some of U2 remain. So we now have residual confounding via multiple different paths. Of course, the hope is that that residual confounding is relatively small because your conditioning approach is maximally efficient. So I'll just briefly mention those two other obscure members of the family, which perhaps don't always get as much attention when it comes to choosing your adjustment set. Now, the reason they don't get so much attention is because, technically speaking, they do not contribute towards bias. And when it comes to the formal theory of DAGs, the thing that we are focusing on is removing bias. Okay, so this is the reason why these things don't tend to get discussed and mentioned quite so much. The first one is the competing exposure. So this is the thing that causes the outcome, but is unrelated to the exposure. As I've just said, it's not a source of bias, but it does explain heterogeneity in our outcome. Now, heterogeneity in the outcome is unexplained heterogeneity in the outcome in particular is not very good when it comes to estimation, because it affects its noise. And that noise is likely to create error and uncertainty in our estimates. So if we are able to condition away some of that uncertainty and error, which is what happens when we condition on a competing exposure, then we could expect our estimate to be more precise. This does not necessarily remove bias, but within our individual study, it will, in theory, improve the precision and reduce the error of our estimates. The problem there is we have to be absolutely sure that that variable is a true competing exposure. And because they tend to be things that cause the outcome, and often tend to be things that are very close to the outcome in time, then there is a risk that rather than being a competing exposure, they're actually a mediator. So here you can see I've changed the color of W so that it's now blue. X is actually has a small path to W. So if we were to condition on this competing exposure, thinking that we're improving the precision of our model, we would actually, unfortunately, introduce bias because we would be closing part of the total causal effect of X and Y. So be very, very careful with these competing exposures. And then the other family member is the instrumental variable. Once again, not a source of bias. So to a certain extent, you could just completely ignore it. And in fact, if it's a true instrumental variable, that's what you want to do, because an instrumental variable explains heterogeneity, not in our outcome, but in our exposure. And we want as much variation in our exposure as possible, because we want to see how does variation in the exposure lead to variation in the outcome. If we start removing variation, it's harder to see that. Okay, so if we were to inadvertently condition on an instrumental variable, then we would actually increase the error and the uncertainty of our estimate, and in fact risk introducing bias amplification, because in a sense any unresolved biases would become even more influential within this sort of tighter space. So the classical advice, if you have an instrumental variable, is that you should not condition on it, because this is going to be the problem that you face. However, the counter advice is, are you sure it's actually an instrumental variable and not a confounder? Because if it occurred before the exposure, why shouldn't it have an onward effect on the outcome? Why would it only cause the outcome through the exposure? And that's the kind of question that you ultimately have to face in practice. That's why this is somewhat of an art rather than a science. Is this truly an instrumental variable, or is it a confounder? And if it's a confounder, I really should be adjusting for it, because it would otherwise introduce bias. So that's the sort of summary headline message. If you're interested in estimating a total causal effect, then 1, you should condition on confounders to block confounding paths. And 2, you should not condition on mediators, as that would block true causal paths and indeed risks introducing collider bias, which I don't have time to explain in full detail here, but I will give an example slightly later on. And then cautiously, you should certainly think about conditioning on competing exposures, because that would improve your precision. However, you need to make sure that it's a true competing exposure and it's not a mediator. And cautiously, you should not condition on instrumental variables, because that would reduce your precision, but you need to make sure that it is definitely an instrumental variable and not a confounder, which obviously you would need to adjust for. So it's a little bit murky around the edges once you move from theory to practice. Once you've drawn your DAG, and I say that as if you just click your fingers and your DAG is made, you then use the kind of underlying rules in order to determine the appropriate adjustment set to estimate your causal effect of interest. So I've already described quite simply how to do that. So for the causal effect of X on Y, given this DAG, then we know that we should condition on the confounders U and C, and optionally on this competing exposure W. Okay, that in a sense is the underpinning of our statistical estimand, because our statistical estimand would tell us that we would need to condition on U and C. We can then move to an estimator. There are a million different estimators that you can use. I show here an example of an extremely simple additive regression model, because most of you will be familiar with regression models, but obviously you can use whatever approach you believe is most appropriate, or is etc., for actually conditioning. So you can see here my regression model. I have regressed my outcome on the exposure plus the two confounders and the competing exposure in order to condition on those. In practice, of course, I'm going to have unobserved confounders like U. So my final estimator may end up being different to what my statistical estimand suggested, because here I've had to swap out U with U2, because U2 is all I've got in order to try and reduce the confounding via U. That's fine, of course, and it's very strongly encouraged and something we would recommend, as long as you make that very clear that this is the reason why you're doing this, you know, and that this is the reason why the estimator has diverged slightly from the statistical estimand. Now, there's a key caveat. When we make a model, let's say a regression model, in order to estimate a causal effect, we do that so that we get the best possible estimate on our for our exposure, right? So the coefficient of our exposure is as accurate as possible. What we mustn't then do, but we're often tempted to do, is to start interpreting the other terms. The other terms in this regression model, y, x plus u plus c plus w, u, c, and w are there to address confounding and to improve precision. They are not there to be interpreted. Only the coefficient on x is there to be interpreted. So the problem is, if we start to shift our gaze and ask what is going on with these other variables, we have lost sight of the relationship between the causal estimand, the statistical estimand, and the estimator. This estimator was built to answer a specific question. If we start, these other coefficients are not interpretable. And the reason they're not interpretable is because they don't reflect total causal effects. So if we were to look at U in this model, it no longer would represent the total causal effect of U, because X is also in that model, and X is a mediator. So clearly will have taken us away from the total causal effect. Unfortunately, that is a very common practice. And that practice of the sort of traditional practice of building a single prediction model for a particular outcome, and then including a whole bunch of variables, and then interpreting the coefficients on all those variables as if they represent some sort of independent associations, has been given a name, and that name is the Table 2 fallacy. And I'm just going to highlight an example of the Table 2 fallacy because I think it's quite informative, but also because it provides a useful example also of collider bias. And I'm going to pick on this paper that was published in the early stages of the COVID-19 pandemic. And I guess the reason I'm going to pick on it, first and foremost, is it was published in Nature, so I think that makes it fair game. And then secondly, because it has actually been dubbed the biggest Table 2 fallacy ever. So I think that also gives you a reasonable reason to use it as an example. So in that particular paper, they did exactly, in a sense, what we recommend you don't do, which is that they created a giant outcome prediction model in which they included a whole series of different so-called risk factors for that outcome. And then they presented those results in a table, and they presented those results also in this kind of visual form. I've only shown a tiny section of that figure, and I'm only going to focus on one particular coefficient just for the purposes of example. I've highlighted that in a box down at the bottom. You can see that current smoking status had a hazard ratio below 1. In other words, current smoking status appeared, people who currently smoked appeared on that, if you were to interpret these as causal effects, to confer a lower risk of mortality from COVID-19. Well, that doesn't make any sense. Doesn't make sense because it's not causal. What's taking place is table 2 fallacy, and specifically a form of collider bias. So we can understand this if we very quickly draw a tiny little DAG to see what's going on. So in this tiny DAG, we've got 3 variables: smoking, lung disease, and death from COVID-19. And we're saying that lung disease is a mediator for the effect of smoking on death from COVID-19, because if you smoke, you're more likely to develop serious lung disease, and in turn, both are likely to cause death from COVID-19. However, there are other variables always lurking. Okay, so I've labeled these U because we don't know what they are really, but there are always likely to be other variables causing the variables within your situation. And in this case, there's likely to be a whole bunch of other variables that mutually cause both lung disease and death from COVID-19. And so what this means is now lung disease is a collider, because you can see it has these 2 paths converging from smoking, and you are both colliding on lung disease. So what did we learn previously? We learned that if you condition on a collider, you will open a conditional dependency between the variables that cause that collider. So here, you would open a conditional dependency between you and smoking. And as you can imagine, that's what's happened. So in the unconditional data, you can see that there is that the coefficient for smoking, the crude correlation, was such that it appears that people who smoke had a higher risk of death from COVID-19. Caveats aside that really you shouldn't be interpreting any of these. Okay. However, in the conditional model, because lung disease had been conditioned on, it had opened that conditional dependency, it opened that collider biased path. And as I've said, that's a kind of weird mirrored path. And it literally was strong enough that it completely flipped the sign. So we went from it being harmful supposedly in the unadjusted data to being protective in the adjusted data. So what's happening there really is that the model is inappropriately adjusted. In that particular model, we shouldn't be interpreting any of the terms whatsoever. And in the case of smoking, the term is so collider biased that it's ended up reversing from what is probably the truth. But in fact, not one of the terms within that model realistically should be interpreted, at least without a DAG, to help us understand what's going on. And that's the reason why that was named the world's biggest table 2 fallacy. Unfortunately, this approach is extremely common. I was trying to look for people who had actually done secondary analyses to kind of identify how much table 2 fallacy was out there. And I've found, certainly it's somebody who did that within dental research found that over half of all of the studies they found were conducting table 2 fallacies. So I've told you what you need to do with a DAG. And I said at one point, once you've drawn a DAG, the problem is I haven't really said how to draw a DAG. The reason for that is we could spend the entire day discussing and debating how you actually draw a DAG in practice. And this is one of the big problems for applied research right now, because clearly there's a lot of excitement and enthusiasm about DAGs, but whilst the rules are relatively easy to learn, as we've just done, drawing them in practice is quite difficult, and it requires multidisciplinary inputs. It also requires, I think, more research and more work to try and help applied researchers work out how to draw DAGs. And that's something I'm trying to do right now, but needless to say, it's a slow process. What I have done a couple of years ago was this review of everyone who had used DAGs in health research up to that point. And we use that as an opportunity to try and offer some recommendations and guidelines on drawing and certainly reporting DAGs more effectively. And in fact, at the end, we produced a table where we offer these 8 recommendations to try and encourage people mostly to report their results and how they use DAGs more effectively, but actually several of those recommendations, in a sense, are also related to how you draw the DAG in itself. However, what we need is something much more like this, the 10 steps to draw your DAG like a pro, and hopefully end up like the toddler there, with great satisfaction in the quality of the work that you've produced. As I say, this is ongoing work, and in practice, I would talk about each of the different 10 steps in considerably more detail, but in the time remaining, I'm just going to whiz through these so you can get a sense of the different features that I think are quite important when it comes to drawing a DAG. So the first of those is an absolute no-brainer, which is that you need to develop and state a clear research question. Now, everyone who's a methodologist or an epidemiologist will have had experience of speaking to someone where you stop halfway through and you say, well, hang on, what's your research question? And this is well represented by this tweet from Sarah Andrea, where she says, hi, I'm an epidemiologist. You might know me from my greatest hits, including, what's your research question? Hang on, let me draw the DAG, and please stop picking your potential confounders based on whether they're statistically significant. Really, in practice, in a causal situation, your research question boils down to what's your focal relationship and what is the causal effect between those two variables that you specifically want to estimate. So what is your exposure, what is your outcome, and what is your estimand? It would be absolutely amazing if we could see this happen more commonly in practice, and rather than when someone comes up with a research question, they actually think about defining those 3 things formally. So just to give some examples from my own research, this would be, say, the total causal effect, that's my estimand, of fasting plasma glucose at 28 weeks gestation, that's my exposure, on the risk of stillbirth, that's my outcome. There we go. I've given you a research question in kind of causal inference terminology. Of course, I can write that in a far more sophisticated way, but at the end of the day, that actually tells you all you need to know. Once you've done that, really, the aim is to go away and to think about your context in great detail. So DAGs are, directed acyclic graphs are context specific. So when you're drawing a DAG, you are trying to describe the data generating process within a particular population at a particular moment in time, right? What is a population? It's the who, the where, the when. Okay, so it's, for example, women attending maternity care in the north of England during 2012 to 2015. When I'm drawing my DAG for that particular analysis, that I need to have that absolutely fixed in my brain. And the reason for that is that obviously, all of the different variables within that context, they may have completely different roles in other contexts, but it doesn't matter. When I'm drawing my DAG, I am trying to describe the data generating context in my specific context. And so, if it's a cause here, if it's a confounder here, etc., that's what matters, not the counterexample of how it might behave in some other population. So, once you've very formally defined, thought about your research question and your context, then my advice is to try and draw the DAG as early as possible. And the reason for this essentially is that the DAG tells us the variables that we need to measure and adjust for. So ideally, you want to be drawing your DAG when you still have an opportunity to influence the data collection process and to help encourage people to measure all of the right variables that you need. At the very least, and in practice, in many cases, where we don't have much say in the actual study design, you want to be involved. You want to be drawing that DAG before you're downloading the data and conducting your analysis so that you make sure you download all the variables you need and you don't have to go back to the data set again and start downloading more and merging more, or maybe even getting more permissions, etc. Now, you can update your DAG as time goes on. And I think this is actually perfectly reasonable. The idea of having a single DAG that never changes is rather limiting. I think it's perfectly reasonable to have an initial DAG that you create at the early stages of the research process. And then as your knowledge improves, and maybe as you get more expert feedback and so on, then you can create second and third DAGs that are improvements on that. However, try and make that process as transparent as possible. You know, if you have a DAG in your protocol and it's different to the DAG in your final paper, then explain, we added these for these reasons, you know, or, you know, because further research demonstrated that these might be important. What you mustn't do, and what it's not just not cool, it's verging on malpractice, misconduct, whatever the right word is redraw your DAG post hoc in order to remove any variables that happen to be inconvenient, you know, either because you didn't have them or because when you include them, they're not giving you the results that you want. Clearly, that's not really in the spirit of what we're trying to do here. That process of drawing your DAGs, ideally, you want to get help. Because as I've said, when we're drawing a DAG, we are trying to use our knowledge and our expertise and our theory to describe the data generating process. And hopefully we do that accurately, because the more accurately we do that, the more accurate our causal estimate will then be. Therefore, you want the maximum knowledge and expertise fed into that design process. So I would argue that drawing a DAG should be a team effort, and that ideally that team includes a wide range of different angles. It includes people who are methodologists and experts in DAGs, and it includes people who are maybe even the public, who are extremely knowledgeable about the specific context that you're interested in studying. And then the other thing that you might consider doing, which I don't unfortunately see very often, but I think I would love to see more of, is people sharing their draft DAG with colleagues, maybe in conferences, maybe online, and saying, please, you know, offer your comments and feedback. What have I missed? What assumptions seem a bit strange, et cetera, et cetera. Because the better the DAG, the better the estimate. And I don't think you can go wrong by including increasing amounts of expertise. The next thing that's very important is that you actually include all of the relevant variables. Okay, so that certainly means all of the variables that cause the exposure, and it probably means most of the variables that cause the outcome. You don't necessarily need to depict all of the mediators if you know there's a whole hat of mediators. But I think as a matter of good practice, it's probably not a bad thing to be complete and include everything. But in particular, you mustn't restrict it just to those variables that happen to be, say, easiest to measure, or that happen to be available in the data set, or that have the least missing data. If a variable can't be observed, and there should always be some variables that you realize that you don't have, then I would explicitly include these as so-called latent variables. So explicitly include them using the appropriate notation for you. If you're using the path diagram notation, then latent variables tend to be circles and ellipses compared with squares and rectangles for observed variables. And the useful thing about that, even if you do nothing else, is that it really helps to highlight the different sources of unobserved confounding. Now, ideally, you will go on and you'll say, well, you know, we have these unobserved confounders, and therefore we've conducted these sensitivity analyses to see what impact it has. But at the least, you have proudly flagged up these are going to be the big sources of unobserved confounding. And just to give you an example, this was from a published DAG in 2015. You can see some of the variables there, such as tobacco use at the top left, have a U next to them, and that means this has not been measured. And I think it's really nice to see this person, almost half their variables have not been measured, but they've been very explicit about that. They show that we haven't measured several of these things. In fact, in practice, it looks like for them, it's not likely to make much, if any, difference, because I'm not sure any of those are confounders. The next thing I would very, very, very strongly recommend is that you draw your DAG in temporal order, right? So a DAG really is depicting the passage of time. It's depicting things happening over time. Now, when I see DAGs, I've seen many that are sort of drawn in a way that's trying to spread the variables out as neatly as possible, or to minimize the number of crossed arcs, if that makes sense. The problem is when you have something like this, I can't tell you really so easily what's going on. I don't know what comes first, what comes next. It's quite difficult to actually read. That's where you need an algorithm really in order to read that. But guess what? You don't need an algorithm if you draw your DAG in time order, because here, which has been drawn in time order, you can see A and B happen first, then C, then D and E, and then finally F. It's so much easier to interpret, so much easier to figure out that, you know, A and B might be confounders because they occur before the exposure. D and E might be mediators because they occur between. And then, you know, you can read that. The other reason that that's important and useful is that nodes are depicting events in time. So you can see we've put A and B here. That means they're happening around this moment. And then arcs are depicting kind of processes occurring over time. So when you draw it like this, it also philosophically matches the underlying theory. So I think it's much nicer. I also think it really helps to reduce mistakes and makes it a lot easier for other people to interpret. But even for you, when you're drawing your DAG, I think it makes it a lot easier to actually draw. The next kind of key feature is that we would recommend drawing all forward arcs in place unless you are pretty confident that they don't exist. So in other words, for any particular variable, you assume that it is a potential cause of all future variables. And so you assume there would be a forward arc, and then you would only remove it when you were pretty confident that it didn't have one, if that makes sense. So clearly, for several instrumental variables, you would assume that in fact it was a confounder, and you would have to be pretty confident that it was actually an instrumental variable in order to remove that onward arc to the outcome. Now, why do we do this? Essentially it's a much stronger assumption to actually remove an arc. Traditionally, we've been reluctant to include arcs within path diagrams in particular, but also within DAGs, because we've been led to believe, you know, you shouldn't really infer causality unless you're confident. But when you're drawing a DAG, you're not inferring causality. You're just proposing the data generating mechanism. And more importantly, when you include an arc, it allows for a causal relationship of any size, even 0. Whereas when you remove an arc, you make a very strong assumption that there must be absolutely no relationship, no causal relationship between these two variables. So it's kind of safer just to leave an arc in, unless you have a good reason to believe otherwise. So next, ideally, although I've never seen anyone actually do this yet, you might check your DAG against your data. And this can be achieved with tools such as DAGTR. And really the idea there is that they just have a quick check. What are the assumptions that your DAG makes? Are there glaring inaccuracies or inconsistencies, more appropriately, with the data set? Does the data set imply that there's a strong correlation between these two variables that your DAG suggests should not be correlated, for example? And that's a step that hopefully we'll see more people doing in future. And then clearly the most, once you've done all of that hard work, use your DAG appropriately. Well, unfortunately, I see people do all the hard work of drawing a DAG and then conduct a massive table 2 fallacy because they think, now I've drawn my DAG. I don't know what they think really, but they don't use their DAG to then select an appropriate estimator, if that makes sense. They don't use their DAG to select the appropriate adjustment set for the exposure outcome of interest. So that's what you need to be doing. And then you need to be stating your implied adjustment sets, ideally within your paper, talking about the sources of unobserved confounding and accounting for that with surrogate confounders or quantitative bias analysis, if possible. And then the final thing I would say, share your DAG with pride. Ideally, share it within your paper. I would love to see papers all include the DAG directly in the manuscript rather than in supplementary material, because you've done a lot of work on that. It is the key assumptions of the analysis. It should be something you're quite proud of, and go on and share. So I'm going to round up and then return for questions. My summary is that I think DAGs are very useful tools for identifying and sharing our assumptions about the data generating process, and that this is essential for quantitative causal inference because they allow us to identify which variables need to be conditioned on in order to accurately and precisely estimate a causal effect of interest. They are difficult to draw in large, complex social science settings. This is an unresolved problem that we need more guidance on. Nevertheless, I can offer these general comments. Drawing them early is good, thinking very carefully about your context, trying to draw them in temporal order, seeking the maximum amount of feedback, and then hopefully sharing them with pride. And then as a final caveat, I just want to say, and this is true of every single statistical approach or analytical approach, DAGs are not a replacement for deep thinking and scholarship. So don't rely on them without thinking. Over-reliance on any tool without thinking will inevitably lead to mistakes. My hope is that by using DAGs, you will think much more carefully about what's going on, and therefore your estimates are far more likely to be reasonable than if you didn't use DAGs at all. I'm going to stop sharing, and I'm going to see if you guys have asked any questions. Georgia. Hello.
I cannot see, oh, there's a question. I was just going to say, I cannot see any questions yet, but one popped up. Very informative talk, thank you. Could you recommend any papers or tutorials to learn more about simulating from DAGs? For example, conducting parameter sweeps and conducting sensitivity analysis for latent variables?
That's a really good question. And not what I can immediately recommend off the top of my head. So I think it's something that I would kind of come back to afterwards with one or two possible papers. I myself simulate data from DAGs. Actually, we've been playing around with a fantastic new Python tool, which allows you to simulate DAGs with amazing levels of complexity, but also DAGTR allows you to simulate with considerably from a very, very simple set of statements as well. I'm aware of at least, I think it was Matt Fox, I'm looking at you, Georgia, who published a paper possibly last year on simulating data from DAGs as well. So hopefully we can come up with a few references that will be useful for you there. It's a very useful thing to do, simulating, because it really helps you to understand what's going on, or more importantly, helps to highlight when you've made a terrible mistake about what's going on.
It is the Matt Fox and colleagues paper, and I think there are a few others. We'll just share them for the follow-up email. The next question says, thank you for the great presentation. Will the PowerPoint and recording be available online? So as far as I know, not online, but they will all be shared with you in a follow-up email after the talk. Yeah,
that's right. So I'll make a PDF and share that. And I think the talk's being recorded. It will be specially available for everyone in Ohio State University. Does anyone else have any questions?
There are more questions. So the next question says, considering the DAG is defined to a specific context and question, please may you advise about publishing a DAG inside of the method section by publishing alone?
That's so sort of, I'm trying to understand this question a little bit, and I'll think out loud, is because it's so context specific, does that make it less relevant within our paper, or what would I advise? I would advise, because in a sense, every study that you do is context specific. It's going to be in a particular population. It's going to be using particular variables. My preference is very much that you include the DAG as one of your figures within the method section. So you actually say, we drew the DAG figure A, figure 1, with the following approaches or the following rules or the following theories, and the DAG implied the following adjustment sets. We adjusted for this using this approach, so it sort of comes a little bit before. I would actually place it before your statistical analyses. What I would tend to do is, describe my population first, and then describe my exposure, then describe my outcome, then describe my estimand, and then describe how I identify the adjustment set, if that makes sense. So it'd be part of the adjustment set identification, and I would then present my DAG, and then I would describe all of the sort of statistical details of how I actually went about and estimated it. I hope that sort of answers the question.
Thank you. The next question is whether you have any recommendations for best and most accessible books, tutorials, or websites for learning how to do causal inference in R.
Well, this is a very good question. I know that Lucy D'Agostino McGowan and Malcolm Barrett, who are working on a causal inference in R book, and I know Malcolm fairly well. He's wonderful and brilliant, and I suspect that guide will be brilliant, but it's not here yet. So we're sort of left with what is available to us, and at the moment there's a sort of bit of a mix between different guides. Depending on your level, really. What there isn't is a really friendly introduction to causal inference. That hasn't been written yet. I dread to imagine the effort that would be involved in doing it, but I have talked to my colleague Ellie Murray about trying to pull together a basic introduction. Failing that, then I would recommend What If, which is by Annan and Robbins, because that is the definitive technical guide to causal inference. The problem with it is, the first time I read it, I didn't really understand any of it. I could read it now and understand it, but only after I had got through that initial learning curve, if you know what I mean. So you're sort of left with to a certain extent, there are some useful papers that might be better starting places. There is also a couple of more friendly books written by the economists, but they're coming at it from an economics angle. So the language is a little bit different, and there's a more of a focus on natural experiment approaches. But again, we can try and recommend a few different source materials. I think that's probably a good idea in the feedback.
Yeah, I think this is maybe a question that can be best answered in the follow-up email. We'll just share some materials, and someone just privately shared with me Malcolm's book online, so on the website, so we can share that as well with everyone.
So a draft is already available, and that's
maybe
that's
I
great.
haven't checked, but I will. The next question is, are there any important differences in DAG construction for cross-sectional case control cohort and RCT-based studies?
That's a very good question. I don't think there's any differences. I think that it's harder when you're working with cross-sectional data than when you've got longitudinal data, because if you think about DAGs, at the end of the day, what you're trying to do is describe the evolution of things over time. And if you're working with a cohort study or even a randomized controlled trial where you might have multiple longitudinal data, then you've sort of already been given some of the answers, because you know when certain things were measured, at least, although you have to think about when they occurred rather than they measured. But even so, you've got some temporal information. When you're looking at cross-sectional data, you have absolutely no temporal information from the data collection process. So you have to provide a lot more external information. I think where they really become problematic is that a lot of variables are evolving commonly over time. So a common question we get asked is, the causal effect of social media use on mental health. Well, these are interplaying heavily over time. So social media use might affect your mood, which might affect your social media use, and etc. the only way to answer that kind of question would be with intensive cohort data, intensive longitudinal data. If you just had single variable that was social media use and mental health, which is what you might have in a cross-sectional study, you can't place it in time because it's just incorporating all of this complex history at once. So I think there's no sort of formal difference between the two, but in general, you'll find it's a lot harder when the variables start to become diffuse in time, if that makes sense.
Thank you. I think these are all the questions for now. We do have some time. Oh, another question. Could you please point to material on application of causal inference and DAGs in economics and finance? And maybe, again, that's one of the things that we can just share in the follow-up email.
Yes, I think we can certainly provide. Economics has a much longer history of using causal inference. So there's a lot more kind of examples of causal inference. However, because of that long history, they haven't embraced DAGs as keenly until very recently. So there are probably fewer examples of DAG papers, but we'll see what we can find and share. I'm sure I know that there will be plenty. Whether they're any good, that's another question. But that's as true of epidemiology as it is for economics.
Okay, one more question has arrived. In your examples, you identified a single exposure and outcome. Is it reasonable to identify multiple exposures, or should these be treated as completely separate estimands and therefore estimated with separate model estimators?
So that's a brilliant question, and it's kind of got a split answer. If you're in a sense interested in a sort of traditional, what is the causal effect of multiple variables on the outcome, then what you might draw a DAG that describes the whole context, and then for each exposure outcome relationship, you choose the appropriate adjustment set for that one, report that one, and then the next one, report the next one, if you see what I mean. So you would then have like a different adjustment set for each total causal effect estimate. If instead you're talking about joint effects / multiple exposure scenarios where you're not interested in sort of the separate effect of lots of different things, but how these things act together, then you get pushed towards more sophisticated analytical methods. Essentially, you have to move towards a joint effect framework, which is either counterfactual mediation analysis methods or G methods. And in that context, what you're then doing is kind of expanding the definition of your exposure to include multiple variables. And you're asking, how does sort of a different combination of these variables then affect your outcome? I hope that answers the question and makes sense.
We do have a few more minutes. I don't see any other questions coming in.
Okay.
Now is the time, now or never.
Last opportunity for a burning question. Yes. So I think that's a follow-up question about would that mediation scenario or that joint effect scenario, would that include interaction terms? Very likely, yes, because as soon as you start asking about joint effects, then you're probably asking about things that are interacting. It seems a bit strange to be asking about, joint effects where they're just additive. So again, within the counterfactual mediation analysis framework, that's a whole afternoon talking about how we do that. Then you would sort of look at the all the variables within what's called an exposure regime, and you'll model any interactions that are present. Of course, they become a lot more difficult to describe, but that's a challenge with any nonlinear kind of effects in general. I think we are coming up to 6 o'clock.
6 o'clock in the UK.
6 o'clock in the UK, yes. So 1 o'clock, lunchtime. In
Yes, it's 1 o'clock here.
Wonderful. Yeah, well, hopefully everyone enjoy a nice lunch, and thank you very much once again for the invitation. It's been a real pleasure.
Thank you, Peter and Georgia. We really appreciate it. And just everybody, in case you have any follow-up about the recording, we will send it out and we will follow up with information in the PowerPoint. So thank you so much for this presentation. We really appreciate it.